What is your current understanding about temperature? Well, for the longest time, we didn't even know as human beings what temperature was. Once upon a time, there was this famous scientist, his name was Antoine Lavoisier, and he said that, you know what, let's imagine temperature as a fluid, an invisible fluid, where you can just pour that heat from one object to the next. And that seems to make a bit of sense, doesn't it? Right? When you touch a hot object, it's almost as if the hot object transfers thermal energy onto you. And if you touch a cooler object, your thermal energy then pours onto the next one. And they noticed that there was no change in mass, so this must be a massless liquid. Seemed to make sense back 200 years ago, but it wouldn't be able to explain one important thing, which is how do you generate heat from out of nothing? That doesn't make any sense at all. And that's what theories are. They're just a way of explaining how the world works until somebody else gives a better idea of how it probably works. And that's what we fast forward to today. Maybe you've heard of this before. It's called the kinetic molecular theory. It's the current theory that we use to describe pretty much everything and how things behave here on Earth, where everything is made up of these tiny little particles called atoms. And as long as you're above absolute zero, they're constantly jiggling. In fact, that's our definition of what temperature is. All right, how quickly these atoms are moving around, because the faster they move, the more or the higher the temperature it is, or the higher average kinetic energy has. And the slower it moves, the less energy it has. This can also be used to describe gases, because by nature, what happens with gases are that the particles just simply bounce off each other and hit against the walls of whatever vessel that it is held in, like a balloon. All right, so all the molecules are constantly hitting the surface of this, and that's what creates this thing called air pressure. It could also be used to describe different states. For example, ice. Ice will be a state where the molecules are moving so slowly that they found each other and they're bond together quite tightly. And as you increase temperature, they create these very loose bonds where they can stick yet fall apart. And that's what it is in the liquid state. You elevate the temperature high enough and they just simply bounce off each other, occupying tons and tons of space. And because these particles are tiny and far away from each other, it becomes invisible, so you cannot see water vapor. If you ever see steam, it's the water vapor condensing around something, and the condensation is what you see as steam. So that's what the kinetic molecular theory is excellent at describing, what temperature is and the different states of matter. And the most important part is that you can drop the temperature to a state that's so low that the particles stop moving and they stop bouncing off each other. And that happens at absolute zero or at negative 273 degrees Celsius. What that implies is that if the temperature of the Earth actually dropped down to absolute zero, if it ever could, then all the gas and atmosphere that's above us, all 300 kilometers of it, it would just all come collapsing down to the ground. We wouldn't have atmosphere anymore, and you definitely cannot transmit sound at negative 273.15 degrees Celsius. We have various different temperature scales out there. One of the original ones that we're more familiar with is the Fahrenheit scale, probably because the guy who invented it was really good at creating a reliable scale that can accurately and predictably tell you what the value of the temperature is. Of course, it was based upon his old scaling system, where many say that he based upon two separate temperatures. One, if you get salty water and you try freezing it, there's a certain temperature where even salt water will freeze. And that's what 0 degrees Fahrenheit would be. And then the next temperature up, where it would be at its max at 100, let's say, that's the average healthy human body temperature at 100 degrees Fahrenheit. Of course, today you'll be saying, well, isn't a kid sick at 100 degrees? Yeah, that's because they reinvented and recalibrated the Fahrenheit scale so it's more user-friendly alongside with the Celsius scale, which I think most of us are familiar with. In the Celsius scale, it is calibrated so that at 0 degrees Celsius, that's the freezing temperature or melting temperature of ice water. And at 100 degrees Celsius, at regular atmospheric pressure, that's when water starts bubbling very quickly, turning into a gas, or where water vapor will condense back into water again. So that's how we calibrated the Celsius scale. I did mention something about absolute zero, meaning that you can't have a temperature lower than negative 273.15 degrees Celsius. So if that's the case, why don't we just reset the scale and let that bottom temperature be at zero? And scientists did invent that, and that's called the Kelvin scale. And the difference between Kelvin and Celsius is 273 degrees Celsius. So at negative 273 Celsius, that's at 0 Kelvin. And at 0 degrees Celsius, it's at 273 Kelvin. Now you know. That's conversion ratio. Oh, Yeah, I forgot to mention, why is it that 100 degrees Celsius, or sorry, 100 degrees Fahrenheit is unhealthy for the human body now? And that's because they had to create a nice, pretty conversion ratio, as you can see right here. All right, so I can't remember which date it was, but at some point they had to recalibrate it, and they wanted to use a nice clean ratio like 9/5 or 5/9 plus a vertical offset of 32. And that way we can have a clean way of converting between Fahrenheit and Celsius. If you remember in the beginning of this course in metrology, we're trying to create standards so that it's universally accepted no matter where you are. So there are certain scale systems that had to be reset and recalibrated again, and that's why there are certain Olympic records that were not valid anymore as a Guinness Book record. All right. For example, inches, they had to recalibrate that as well, so that 1 inch is exactly equal to 2.54 centimeters. And a Celsius and a centigrade, they're roughly the same thing today. Some may argue they're off by 0.01 degrees.
This isn't energy! These are absolute 0-degree molecules!
Whoa! 470 degrees below zero in there.
All right, 2 gripes about it from every science nerd. First off, Megatron says these are absolute 0-degree molecules, and this is here on Earth. And as far as we know, we can't contain anything at absolute zero here on Earth, because as long as it makes contact with something that's not at absolute zero, it's going to gain some of that thermal energy. All right, so that's one thing that's very difficult to attain. Even though you can stop one atom, which they have been able to do, good luck trying to stop a group of them without them touching another object that which is not at absolute zero. And the second gripe is what was stated by Astrotrain. Whoa, 470 degrees below zero in there. Ha 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 ha. All right, fair enough. This is an American TV show, but if you take a look at degrees Fahrenheit, the lowest temperature ever possible in Fahrenheit is negative 459 degrees Fahrenheit, not 470. So how exactly is that possible? Well, I scoured the internet, and there are a bunch of super nerds debating upon it, and they did quote something that's very important. If you read what Astrotrain said, he never mentioned any units. You don't know what unit it is. For all we know, it could be Cybertronium units. Right, Astrotrain? Yeah, that's right. Okay? And that's why it's so important to have an international standard in our measurements and include units. Yes, when you're talking about degrees Celsius, please include that circle. Don't just say it's 23 room temperature. Write down 23 circle C so that we know that it's in degrees Celsius. And if you want to convert into Kelvin, then add 273 with that, so that will be at 296 K. And interestingly enough, with Kelvin, you don't put a circle with that. And no, degrees Celsius, degrees Kelvin, and degrees Celsius, Kelvin, and degrees Fahrenheit. No, those aren't the only temperature scales out there. There are tons of them available. In fact, even Sir Isaac Newton tried to create his own. Only problem is that when the scientists tried to figure out how it relates to the rest of the world, his calibrations were far out of whack, and that's why many people favored the Fahrenheit scale, because it was fairly accurate and reliable, which is one of the important things with regards to science and data collection. As for Cybertronian scale, I don't think we really know any other value of it because it was never mentioned again, but we do know that it starts off at negative 470 and goes up from there. There are 3 different methods of heat transfer. If you ever held on to a hot cup of coffee, if you don't have a thermally insulated container, you'd be able to feel the heat, and that's transfer of energy through conduction. So with the hot water you've poured into the cup, the molecules are moving very quickly as it is at a higher temperature. They beat against the surface of your container, and the molecules of your container start jiggling very quickly. And those end up transferring the thermal energy onto your hand. And that's through conduction. Heat conductors are really good at transferring thermal energy, such as metals, and believe it or not, diamond is one of the best thermal conductors out there. On the other end of the range, if you want something that which you won't get, 3rd-degree burns on your hand, then you'll need a thermal insulator. Yes, air is pretty decent at it, and that's why there are those sleeves that you have on your coffee cups to gap you and the container by air. And that's exactly what happens in these type of containers over here, these double-walled insulated containers. It's not a solid piece of metal. There is an air gap between the two, and even better, if you're able to vacuum out and suck out all the air, it works even better, because without air molecules, then there's no medium to transfer the thermal energy from point A to point B. Convection is what happens in this crazy gizmo, if you've ever seen it before, these lava lamps. There's usually a light bulb at the bottom of the lamp, an incandescent light bulb. It creates a lot of thermal energy. With that thermal energy, it heats up the wax, causing its molecules to move faster. And according to the kinetic molecular theory, if it starts moving faster and faster and faster, they need more space to do their workout. And what results is that the medium starts to expand. And as it expands, its density decreases to the point where the wax is less dense than the water. Here we're on Earth, and we know that gravity loves to grab onto things. You might notice that between rock and water, rock gets pulled down and water gets pushed up. It's the reason why air is up above. All right. If you ever owned an aquarium before and you try blowing bubbles down below, you'll see the bubbles rising up because gravity loves the more dense water than the less dense gas. And that's what's happening in your lava lamps. As you're heating up the wax, it becomes less dense than the water to the point where it floats up. Where it's further away from the light bulb, it begins to cool down to ambient room temperature, where it becomes dense enough where it's going to sink back down again. And that's the very reason, if you ever have any sort of baseball board heater, so those heaters that are at the bottom of your house, they place them on the bottom on purpose because we know that heat naturally rises. On the other hand, if you have one of those newer retrofit air conditioners, you'll notice that the way how they mount them is that the evaporator unit is placed up above, near the top of your wall, because cool air will sink. Now you understand the science of how houses should be built. And the third method of thermal energy transfer is through radiation. Sometimes we can see it through visible light, but there are other wavelengths of light that we cannot see, such as infrared light, which is emitted by lots and lots of lighters. I thought I had one over here. Yes, I do. All right. And the reason why it feels really warm up here is because there's a lot of infrared radiation being emitted. You don't believe me? Get a Wii remote, and you'll notice the Wii remote actually tracks the cigarette lighter or any candle, because in the Wii remote itself, at the front, that black part, that's actually an infrared camera looking for any infrared light, and that's what you're placing at the front of your TV. Now you know. Every piece of matter has a different specific heat capacity. In other words, the amount of energy required to heat it up and how well it can retain that energy afterwards. There is a lookup table for this. Some substances are really good at retaining heat, and other things are terrible at it. For example, with regards to air, if you look in the list, air usually has a very low specific heat capacity, and that's why we like to use air as an insulator, because it doesn't take much energy to heat it up, and also it's really terrible at transferring the energy from point A to point B. Only vacuum space would be better than that, really. All right. Same is also true if you've ever purchased one of those jackets that are filled up with feathers. The feathers create these little air gaps that don't move, meaning that the air is trapped so that the thermal energy can't easily transfer from point A to point B. And that's the reason why you probably want to include film on top of your window in the wintertime, so that not only does it block any additional drafts, but it creates another thermal barrier where you have stagnant air that's not able to freely move and thermally transfer heat from one side to the next. Water, on the other hand, if you look at its number, I know it's written in scientific notation, but this number, and when expanded out, is roughly around 4200 in comparison to, for example, I don't know, liquid nitrogen, which is at 110 in the scale over here. All right, so what this means is that water, it takes a lot of energy to heat it up, but afterwards it holds onto the water for the heat for quite some period of time. And that's why with a hot coffee cup, if you started off with one at the beginning of this video, it's still relatively warm, even at this moment over here. On the other hand, if you fill it up with, I don't know, air, let's say, and you heat it up, by now it's at ambient room temperature. If you ever used a hairdryer before, you'll notice that the air is really hot when the air first escapes, but if you try trapping in a bag, it will cool down quite quickly. As for how much energy is required to heat up an object, it's based upon this generic formula over here. Obviously, the greater the amount of mass you have, the more energy is required to heat it up. So if you have double the mass, then it'll take double the energy. C is that magical constant for how much energy it takes to heat up 1 kilogram of that object by degrees Celsius, and delta T is the change in temperature. All right, so a change in temperature of 10 degrees versus a change in temperature of 20 degrees from your reference, well, to increase it in an object's temperature from whatever its baseline is up by 20, it'll take twice as much thermal energy than it does to increase it up to 10 degrees. So in other words, temperature is a linear scale. It's a linear correlation. That's why you don't see any squares in the formula. In your textbook, it doesn't write the formula out like this. Instead, it replaces EH with the letter Q. And the reason for that is because Q, by chemistry definition, it's not a state function. It's a path function. It's a fancy word for saying that this only tells you change. It doesn't tell you an absolute value. All right. So Q only tells you how much energy needs to be added in order to heat up an object, or how much energy needs to be removed to cool an object down. Let's go through a mathematical example. How much thermal energy is needed to heat 80 liters of water from 15 degrees Celsius up to 24 degrees Celsius? And let's pretend that the bathtub is made up of styrofoam. Reason for that is that styrofoam has not only a low specific capacity, it also has a low K constant, or its thermal conductivity. It's not good at transferring thermal energy. Otherwise, you have to factor that into your calculations, and it gets rather messy. So in this problem over here, we only need to write down the formula just once. But if the bathtub was made up of, I don't know, let's say iron, then you'll need to have another MC delta T to factor in for C for iron, and then the first C for the water itself. Word problems always start off with givens. So what is the mass of the water? Originally, the definition of a liter was formed by taking a container that's 10 centimeters by 10 centimeters by 10 centimeters and filling it up. That's the definition of 1 liter, and it still is true to this day. What about 1 kilogram? If you get distilled water at 4 degrees Celsius and you fill this up to the top, that was our original definition of what 1 kilogram is. So in other words, 80 liters of water is roughly equal to 80 kilograms of water. It's not spot on perfect because as you increase the temperature, it thermally expands, thus its density decreases, and its overall conversion is not accurate. Right? But for our purposes today, let's just say they are roughly the same. So we have roughly 80 kilograms of water. As for the heat capacity of water, depending on the textbook you have, some will state that the value is 4,200, others will be 4,190, and yet others will be more picky at 4,186 because that is conversion ratio between joules and 1 nutritional calorie. For me, it doesn't matter if you use this value over here or this value over here because this science over here isn't 100% accurate. It's good to within 1% accuracy, and that's fine for most observations. So I'm okay with either 4200 or 4190. Delta means a change in. So it's a change in between final subtract initial. Remember, always subtract the final from the initial. So the final temperature is at 24 degrees Celsius, and the initial temperature is at 15 degrees Celsius. 24 minus 15 gives you 9. And grammatically speaking, it should be 9 Celsius degrees. 15 degrees Celsius is a state. It's what the current temperature of the room is at, or what the water is at. How do you get up to 24 degrees Celsius? By increasing it by delta of 9 Celsius degrees. So that is your path value. All right. Not that I'm very fussy about that on any quiz, test, or exam, but I'm just letting you know that that grammar actually exists in science. The position of where you place the circle matters. So then what exactly is Q, the path function, or how much energy must be added to heat this up? Well, Q is equal to MC delta T, a linear correlation function. Sub in all the values, crunch away, and then you get an answer. A massively huge value. Keeping in mind that 1 joule is equal to taking a water bottle and lifting it up 20 centimeters. So now you need to lift it up 3 million times to heat up this water from 15 degrees to 24 degrees Celsius. Mind you, this is a lot of water, so it's going to take a lot of energy. One last thing to mention about is that because Q is really a delta at the end of the day, it really just tells you a change in value. It could either have a positive answer or a negative answer. And what you'll notice is that when you go from 15 to 24, you have a positive answer. And what that means is that if you need to add heat, then your Q will be positive. If it's going to release heat into the environment or onto another object, then Q will be negative, or Q will be less than 0. James Prescott Joule, again, the dude where we name energy in honor of, he was really focusing on thermal energy. He created this crazy contraption just to prove that thermal energy is the same as mechanical energy. So this is a paddle system that's able to swish water around like crazy. And one of the interesting things about swishing water around like nuts is that you can actually increase the temperature of the water just by swishing it around. In fact, if you're crazy enough, you can actually shout into a cup filled up with water and it will thermally increase. I've done the math. It'll take you a couple hundred years to get that done. So don't bother shouting at your cup of coffee, hoping that'll heat up. They say it takes about an auditorium of people shouting all at once to eventually heat up water or a coffee from room temperature to an enjoyable temperature of probably 50 or 60 degrees Celsius. So in this contraption over here, James Joule, he let a mass fall. So this is a delta E in the form of mg delta H. And there was another delta E over here, which we call Q, which is equal to mc delta T. So we're converting gravitational potential energy into thermal energy. And it is totally possible. And if you've ever been to Costco before and tried out their yummy free samples, maybe you've met Jim before. Here's Jim. I don't know if his name's really Jim or not. I found this picture on the internet. But if you've ever tried out this from that particular food blender, what the person does is that they turn on the machine. It's really loud and really jarring, but it spins the food so quickly that it causes the food to heat up. So there's no heating element inside here. There's no coil heating up the liquid itself. It's simply a blade spinning so fast that it bumps all the molecules so quickly that their average kinetic energy increases. That's pretty neat, isn't it? Also, one more fun fact. Can you measure temperature based upon one atom? The answer is no. Why not? You got to look at the definition of what temperature is. Let me just rewind back. Temperature, by definition, is the average kinetic energy of a substance. Oh, all the way back here. Huh. All right. A temperature is a method to measure the average kinetic energy of all the particles in a quantity of matter. So that's why you can't measure temperature with just one atom. In fact, even in a container like this, not all of the atoms are moving at the same rate. Some are moving faster and others are moving slower. It ends up creating a bell curve. And what you're looking at is the average of that bell curve. And that's the definition of what temperature is. The average kinetic energy of the molecules in a given substance. One more thing to think about before we move on to our last problem. We learned this already. In an isolated system, total energy of the system is equal to zero. In other words, any change in kinetic energy plus any change in potential energy will net to zero. This is true of taking any object and throwing it up into the air. As long as you're not catching it at the end, and as long as it just remains airborne, the energy inside here remains constant. So if you launch this at 1 joule, this will always contain 1 joule. Initially 1 joule of kinetic energy, then 1 joule of pure potential energy, and gradually increasing back up to 1 joule of kinetic energy again. Delta means change in, so delta EK means 1/2 MVF minus 1/2 MVI. Same as delta EP, that's equal to mg delta HF minus mg delta HI. Before you go off factoring or anything, I'm just trying to explain a general concept. Let's say that we decide to bring all the negative terms over to the other side. So negative 1/2 MVI becomes positive 1/2 MVI, and negative mg delta HI becomes positive mg delta HI. Finally, let's do a swap-rooney of all the objects from left to right and right to left, get rid of the minus signs on both sides, and now we have the same formula that we talked about in the last class. I'm showing you this because we need to use the same concept with regards to thermal energy. So in other words, if I have two separate containers, one of hot water and one of cold water, and I mix them together, well, I'm not adding any energy to the system. They're just simply exchanging the energy between the two. So the total energy of the system remains the same, but you do get lukewarm water at the end. So the conservation of thermal energy states that you take a bunch of liquids, you mix them all together. If it's an isolated system, it'll net to a value of 0. The textbook would simplify and just write down something like this. Thermal heat released by one object plus the thermal energy absorbed by the second object will equal 0 joules. In fact, some textbooks do this other weird thing, which is negative Q released, as the minus sign reminds you that energy is being released by one object, is equal to Q absorbed. And I don't like this definition because it misses out on the emphasis that it's an isolated system and it nets to a value of 0. All they did was they took this term and brought it to the other side, and it became negative. Okay, but I hope that you understand the true meaning of this formula now. Armed with that knowledge, let's solve Calvin's problem. He says the water is too cold, so the mom needs to add some extra heated water. Or is it the other way around? Oh, the water's boiling. All right, so Calvin doesn't like the hot water, and he wants it to cool down. Normally, this is known as an open system. Why is it an open system? Because we don't have a sealed container on top. In other words, with the water itself, as they're moving very quickly, if they want to cool down, all they need to do is knock some water molecules to the point where they become water vapor. And that's how things cool down. So in other words, if you're really sweaty, the reason why you have sweat in your armpits is that the water in your armpits is hoping to evaporate. And the only way for it to evaporate is to change its state from this to this. So it needs to steal and take the energy from something like the human's thermal energy from your human body. So as it takes the heat energy from your human body, then it's able to evaporate. That's why you cool down when you sweat. All right. So if we put a lid seal on this, and let's say that this bathtub is not made of metal, but it was filled completely with styrofoam, now we have an isolated system. So let's just start off this problem as hypothetically if it was an isolated system. So you have 100 liters of water at 30 degrees Celsius. Kelvin doesn't like that. He wants it to be dropped down to 24 degrees Celsius. How much extra cool water must be added in? And let's say the cool water was at 10 degrees Celsius. Let's work away at this. And my recommendation for solving these problems is that whenever you have multiple objects, create different groupings for your givens. So you have your givens for the hot water and you'll have givens for your cool water. And you'll just fill it up and populate it away until you have a question mark somewhere. And that question mark is what you're trying to look for. All right, so let's work through this real time together. The bathtub has 100 liters of water at 30 degrees Celsius. So that's the hot water. And we know that 100 liters is roughly equal to 100 kilograms. So mH is equal to 100 kilograms. Water has a heat capacity of 4190 joules per kilogram per degree Celsius. And that's the same down here as well. As for the hot water, it started off at 30 degrees Celsius. So TH is equal to TF minus TI. So the final temperature, we want it to be at 24 degrees Celsius, but it was started off at a scalding 30 degrees Celsius. And if you do 24 minus 30, then you get negative 6 Celsius degrees. The hot water is losing energy. That's why there's a minus sign. As for the cold water, we don't know what the mass is. That's what our require is. So just put a question mark, and that's sufficient. The reader knows that's what you're trying to look for. As for the change in temperature of the cold water, it started off at 10 degrees Celsius, and we want to raise it up to a final temperature of 24 degrees Celsius. 24 subtract 10 gives us 14 Celsius degrees. Awesome. On to the next part. The formula is mc delta T plus mc delta T is equal to 0 joules. One for the hot water and one for the cold water. As we're trying to isolate for mc, we need to take this term and bring it over to the other side. And that's why with some teachers, you'll see that they just have a minus sign on the other side. That's the reason for it. It's because it's been rearranged for you. All right, but I really want to share with you the origins of this, because I take it that if you're taking physics, at some time you'll need to take this course called thermodynamics. And thermodynamics always assumes this for an isolated system. It's whatever you add up equals to 0. So I just want you to start by doing this good form. Okay, even though we know that at the end, when you bring it over, it is going to become negative. So M hot water, which is going to lose thermal energy, CH delta TH. Divide both sides by MC, oh, not MC, C delta TC. Solve for MC. Sub everything in, calculate it super carefully away, and even though you need to show your work like this normally, I hope that you know that in your calculator, you're wasting your time typing that in twice. So in your calculator, you'll just type in 100 times negative 6 divided by 14. And, oh, yeah, units always have to work out. All right. You shouldn't have a negative mass, because if there's a negative mass, either you need to find some antimatter to get the job done, or the solution's impossible. All right. So there you go. That's why the math has to work out. The negative signs have to divide each other out some way or another. All right. So negative times negative gives you a positive answer. So you need to have positive 43 kilograms of cold water filled into the tub to drop the temperature down to 24 degrees Celsius. And now you know how to solve some questions in tonight's homework. For more adventures like this, I guess stick around. Let's start taking up some of the homework questions. All right, do I have my givens here? Awesome, because we know that it's going to gain, so that's why it's a plus sign, 2.47 times 10 to the 4 joules of thermal energy when it's finally heated up to a temperature of 150 degrees Celsius. So how cool was it at the beginning? We know the formula is Q is equal to MC delta T, or TF minus TI. And what we're trying to do is that we're trying to slowly rearrange and isolate for TI. First thing we got to do is that we got to get rid of anything beside any bracket. So that's why we divide that out first. And the quick way to get to the next line that I normally do is that if this is my final answer and it's negative, how about I bring it to the other side to make it positive, and everything on the other side, bring it over so that it becomes a negative term. Beyond here, you sub and solve, and you'll get to your correct answer. Number 2, we're trying to look for the final temperature. So whenever you mix cold and hot together, how do you solve these problems? First thing you want to do is that you want to fill in your given tables, either like this or like this, it doesn't matter. So you'll have givens for your aluminum, where you know that the aluminum is 100 grams starting at 15 degrees Celsius, and then you have to use a reference table to look at the heat capacity of the aluminum, which is usually at 910 joules per kilogram degrees Celsius. Is that the case here? Yeah, because depending upon the quality and the nature of the aluminum and how its lattice structure is formed, you might have different answers for the heat capacity of aluminum. As for those crazy details, you'll learn that in university. All right, so for now, just use that reference lookup table that I give to you, or whatever your teacher gives to you, and use that as your standard for aluminum. And when you look at this problem over here, the only thing we don't know of is T. So that's when this problem over here, it will require a lot of arithmetic rearranging to get to your correct answer. We know that MC delta T1 plus MC delta T2 should net to a value of 0. Or if you want to bring one of the terms over and make it negative, that's up to you. It doesn't really matter. When we populate everything in, this is messy. And my recommendation from here and beyond is always to multiply these two first. You know that's going to be your T. So 10% of 910 is 91T. That same coefficient will be brought into the 15, and that's why once I've calculated out the 91, I'll just take the 91 and multiply it by 15 to get to my next term, 1365. A quarter of 4190 will give you around 1,000. So 1047.5 T, because I'm going to group these together, multiply by T, but that group is also going to be multiplied by 95, so I keep this answer and multiply by 95, paying attention to the sign that I have there. So this is negative 99512, I believe. 513, I suppose. Joules is equal to 0. Now we carefully bring these terms over because we want to collect like terms. So those two negatives go over, they become positive, and we add the 91 with the 1047, which did I show that here? Yeah. Slowly isolate for your T, and I believe the answer for this one is 88 degrees. Yeah, 88.6 degrees when you carefully rearrange this. In this question over here, we're trying to look for, it's kind of like the bathtub example. We will need to figure out how many stones are needed to increase the temperature of the sap. This is one of the traditional ways of boiling things. You heat up the rocks and you drop the rocks into your soup or your sap. I always recommend that you have different givens for the different objects. So you have the givens for the rock itself and givens for the sap. They said the sap is similar to that of water, so that's why we use this number here. And the rock is similar to that of sand, so we're using this as our specific heat capacity value for the rock. The rock starts off at 1,000 degrees Celsius, finishes off at a cooler 85. The sap started off at 60 and heats up to 85 degrees Celsius. So that's why you'll notice over here, if you want to be grammatically correct, it increases by 25 Celsius degrees. Meanwhile, the rock itself decreases by 915 Celsius degrees. Again, I'm not a huge stickler about this, but if you get into the world of thermodynamics, they're pretty fussy over there. You take the formula, Q1 plus Q2 will equal 0, isolate for the mass, sub very carefully in and solve, and you should have a positive mass. If you have a negative mass, either you made a mathematical mistake over here, or you forgot the minus sign here. As for this question here, it's just the wording you got to watch out for. You'll notice the water started off at 38 degrees Celsius, but then dropped by 10 degrees Celsius. And we want to bring the water back up to 38 degrees Celsius again. So as for the cooler water, it started off actually at 28 degrees Celsius, and we want to bring it up to 38. That's why we need to increase it by 10 Celsius degrees. How much hot water must be placed in? And the hot water will be at 80 degrees Celsius, and we want to bring it down to 38 degrees Celsius. Now that you have all your givens, it's just like the previous example with the sap, you're isolating for M. If you want to save some time, as this is a relationship between water and water, you can show me that strike, that they go to 1, and I'm fine with that. That way I know that you know that they're the same value, and it's unnecessary to type it in just to divide by that same number again. Number 5 involves a little bit of know-how from the previous triad of this unit in the world of mechanical energy. All right. So the heater is able to deliver thermal energy at a rate of 200 joules per every given second. So after 60 seconds, there's a certain amount of thermal energy that's been given to the object. Right? The thermal energy is equal to the power times time. So 200 watts times 60 seconds gives you 12,000 joules. That's the amount of thermal energy that is then delivered into the water itself. So P delta T is your Q, the thermal energy you're adding to the system, and that's equal to MC delta T. And that's why we need to be careful with our T's. We'll reserve capital T for temperature in this case over here, since we're very used to showing delta lower t as time. I know that T can also be used as a period, but period usually doesn't have a delta beside it. So that's the only way you can differentiate between them. Anyways, you're trying to solve for the heat capacity object, so if you want to do it in one shot, you could. P delta T over M delta capital T, sub and solve, and you'll be able to find out the heat capacity of this mystery liquid. A sample of aluminum was heated and placed into an insulated container of water. If the final temperature is 35 degrees Celsius, what is the magical heat capacity of the aluminum itself? In fact, the story behind this I'll cover in more detail in the next lesson. But let's just go through the calculations right now. Make sure that you have givens for your aluminum and you have givens for the water itself. We're trying to look for the heat capacity of aluminum. So aluminum started off at 153 degrees Celsius and then cooled down to 35 degrees Celsius. So it lost thermal energy. That's why there's a minus sign. As for the water, it gained heat, and that's why your delta T is positive. Q1 plus Q2 equals 0. We're isolating for C aluminum, so we bring this term over, divide everything by M delta T. Sub and solve. As for the last question, it's just a simple conversion. We know that negative 273 degrees Celsius is equal to 0 Kelvin. So at 100 degrees Celsius, it's 273 plus 100, which is 373 Kelvin. And you do the same exercise for the next few. All right. Or when you're converting Kelvin to Celsius, you subtract 273. 27 degrees Celsius. Often, as for laziness, with some calculations, they just assume 300 Kelvin. Why 300 Kelvin? Because it's close enough to ambient temperature for human beings, at least. Now you know. Catch you in the next episode.